All right, welcome back. Thanks for coming back from lunch. My name is Farnoosh Banai-Kashani. I'm an organizer, one of the co-organizers of this symposium. It's with great pleasure for me to introduce Dr. Fernando Perez, our keynote speaker for the afternoon. So Dr. Perez, I just learned that he just got his tenure and with promotion as associate professor. So actually in my notes, I have assistant professor, but associate professor in statistics at UC Berkeley. And also a faculty scientist in the Department of Data Science and Technology at Lawrence Berkeley National Lab. Fernando got his PhD in particle physics at UC Berkeley. And at U Boulder, so welcome back. So welcome back. And also, thanks for creation. Postdoc in applied math. Now, his research focus area is in creating tools for modern computational research and data science. And this part, I'm sure you have worked with his research outcomes. See, he's created IPython while a graduate student. This is a note to my graduate students, by the way, and myself, of course. And also co-founded the Project Jupyter. And he has many titles, including a fellow of National Academy of Science, as a senior fellow and founding co-investigator of BITS, which is Berkeley Institute of Data Science, and a lot more. So I'll stop there. Without further ado, let's welcome our speaker, and please.
Thank you, folks. It's a pleasure to be here, to be back in Colorado. I had never actually been to the CU Denver campus, but I was in Boulder for 12 years at CU, both as a grad student and postdoc. So thank you to the organizing team for inviting me. I want to credit my co-author in these materials, my postdoc Lindsay Hagee, who's done a huge amount of work on all of these ideas with me. And so, is this working? Oh, they work a lot better when you turn them on. So I've had a very odd career. I did my PhD at CU. I was working on a very, very dark alley of theoretical physics called lattice QCD, dark enough that it nearly killed me. I was pretty much destined for a disastrous non-PhD completion. On my 5th year, my PhD advisor fired me, and I started hacking for fun as a way of productively procrastinating. That led to IPython. I did finish, I did graduate thanks to a second fantastic advisor, Anna Hasenfratz, a wonderful Hungarian theoretical physicist who helped me basically finish up with a project that I could graduate with. A lot of my time was really spent. This is up in Rocky Mountain National Park. This is in Utah. That's really where a lot of my time was spent, which probably contributed to me not being very successful in physics. My postdoc was in applied mathematics. At CU Boulder as well, working with Greg Belkin on numerical algorithms for PDEs. Very numerical, kind of traditional applied math work, all of it Python-driven. So it became kind of a space to actually build, and this was 2003, 2005, 2007, kind of really getting involved into building the open source and numerical computing ecosystem at the time, driven by concrete research in applied math. But through weird connections, that led me to going to Berkeley first, to work with neuroscientists. When they invited me to go and participate on a project, I had to borrow a book about what was an MRI scanner to read on the plane because I literally had no idea what they did, and I landed to supposedly work on a large grant proposal with them on that around open tools for neuroscience. That led to a few years later moving to Berkeley, working in that field for a while, then becoming part of the team that designed and put together the Berkeley Institute for Data Science with funding, as Kevin explained, from the Warren Sloan Foundations. And eventually I became faculty in stats, and as it so happened a few weeks ago, got tenure with this completely bizarre path, right? My CV looks like a mess. I'm basically unhireable by almost anyone under normal premises. And so part of what I want to talk about is how did I get here, and what is it that makes this space of data science an interesting one with these weird intersection of profiles, and what happens to the tools that we need to use for this. I've used this as one of my kind of driving stars, kind of guiding stars. It's an old quote from Hamming from the 60s. He was worried about computers producing too many numbers too quickly before people understood them. You can imagine he was probably worried about less computing power than any of us has in our pockets today. And so the role of tools that help us actually think, not just crunch, not just manipulate, but actually think and produce insight and analyze and communicate is very important, and that's kind of the space that I occupy. I'm not really working on numerical algorithms anymore. And I want to talk a little bit about what Jupyter is from this perspective, paraphrasing Maslow's hierarchy of needs, around what makes an open source tool at the scope that we're talking about with Jupyter, because it's not software, actually. It's not open source software. It's not code that matters. That code powers and supports things like public services that are available to the public and that drive content, which is ultimately what people want. They want to understand things, they want to say things, and so there is this weird, difficult, tricky tip that I don't have too much time to spend on, but that is very important, I'm happy to talk about. But additionally, for us, the project has taken enormous amounts of effort into extracting and abstracting out as public information, as publicly documented ideas, standards and protocols that the software we produce is an embodiment of, but that others can replicate, that others can implement, that others can produce, which supports actually a broader community, a healthier community, a more creative community. And finally, those things are built by a community of people. And it turns out that is the most complicated part of these efforts at this scale. And I'm very happy to have been invited here by a business school because in a sense, this is a business and organizations and economic incentives talk. It's not a software talk. And hopefully we'll get to that and we'll see what, and I hope to have useful conversations with all of you around that. So in terms of services and software, we build things. Troy already did a phenomenal job. Thank you, because you gave a much better talk than I would around what Jupyter is and its capabilities, so I don't need to belabor. Save me like 5 or 10 minutes of talk. We have Jupyter Hub. We also have tools like NB Viewer and Binder that allow us to run services for you to share your work. So NB Viewer is a way of giving someone a viewable version of a notebook that you have somewhere online without them having to install anything. Binder gives you a way of giving them an executable version of that, and we'll return to that and why that's important. As the notebook machinery evolves, we have just released a few months ago a new version called Jupyter Lab, which is basically the distillation of the lessons that we've learned around interactive computation with the Jupyter machinery over the last few years. It's been a huge collaboration between the open source community, the Anaconda company, and especially the team at Bloomberg Tech, who has done a spectacular work, and it is an example of an interesting, sustainable relationship between industry and the open source community. I would love to get a lot more into Jupyter Lab. It deserves its own talk, but it's not the topic of today. As I mentioned, this software embodies ideas that are generic. So to reason a little bit by analogy, you can think of the web as fundamentally anchored, in a highly simplified version, fundamentally anchored around the protocol of HTTP that allows servers and clients to communicate, and that protocol is typically used to have a web browser talk to a web server, but it doesn't have to. You can, and many people do, build many other services over HTTP where there is no web browser, there is no web surfing happening. It's other things are happening transported over that protocol. That's the value of having a proper standardized protocol, not just a custom service where the AOL client talks to the AOL network the way kind of the broken AOL pseudo-internet used to be. And then when that content is meant for human consumption and rendering and presentation, we encode the data of that under the specific format of HTML. So we have sort of a similar analogy in Jupyter. There's a protocol which describes how do clients talk to computational processes. What does it mean to execute a bit of code and get an answer back? How does that, it seems something very simple, like, well, you type some code and you print the answer back. Turns out there's a little bit more to it than that, and we've taken lots of pain to documenting and kind of dissecting that idea and making that explicit and independent from our implementation so that others can implement it. And when that dialogue between you asking for something to be executed and some process, some programming language running that code is meant to look like a document to you. There's a human story to it. We have a document format called the Jupyter Notebook format that can encode that as a document, and then it can transform it. It's full of metadata, et cetera, et cetera. This idea of a protocol and of making an explicit protocol is what led from IPython to Jupyter, because this project began in IPython, but at some point we realized nothing special. I mean, I love Python. I do all my work in Python. There's nothing special about Python at this point. And here, this is about sending something code to run and getting an answer back from it. Who cares what language it is in? But the code is sent as text. And whatever the answer comes back should be in a standardized data type. So we could do that in Julia. We could do that in R. Julia, Python, R are the three open languages of data science, and they're kind of the inspiration for the name of Jupyter, because that's kind of where we were going. But by making it a protocol, we did work with the Julia and R teams into implementing that protocol with Julia and R backends. But today, there's over 100 different, we call them kernels, Jupyter kernels. There's over 100 different implementations. I think they cover more like 80 languages because there are multiple kernels for the same language. The kernel count is like 110, 120. The language count is probably a little bit less than that, but it's close, probably close to 100. Most of these we have nothing to do with. Many of them are weekend toy projects, but a number of them are real serious production tools. That's the value of building an open standard that an entire community can embrace. And then finally, that community you also have to spend time on. People take a lot more management, they take a lot more effort than machines, as is no surprise in a business community. IPython, yes, it was born as an afternoon hack. That's what I told my advisor. I'm gonna play with this Python thing for an afternoon. I'll be back to work tomorrow. It's been 20 years and I never came back. So that's kind of the quality of my time estimates. Don't tell that to program officers when I submit grants. There, my timelines are perfect. It was born as a toy little Python script at the beginning. That's the very, very, very first version of it, which was 250 lines of Python when I was a grad student at CU. But anything that I'm going to show you today would be completely unthinkable as the work of a person. It is only possible because we have a huge and very, very diverse community of people participating in this from multiple angles. So these are pictures from our annual developer meeting from March of this year and from last year. This one in DC, this one at Berkeley. And there are people in this picture, in these photos, who come from, let's see, Microsoft, IBM, Google, Amazon, Federal National Laboratories, Netflix, Simula Research Lab in Norway, DESI, which is a particle accelerator in Germany, UC Berkeley, Cal Poly San Luis Obispo, UC Merced, and independent members of the community. So you have the biggest tech companies on earth, federal lab, large-scale federal labs in the US and Europe, universities, both large R1s like Berkeley, and smaller universities like Cal Poly and UC Merced, and individual contributors, volunteer contributors who participate from the community. And nurturing something like that takes a huge amount of work, but that is what gives us our strength and our power. We have spent a ton of time on this. We've spent time developing full-blown governance models and developing models for managing. We're not perfect. We've made a lot of mistakes, I promise you. But at least we have done a lot of work, human work, community work, even legal work. I'm one of the co-founders of NonFocus, a 501c3 that plays a role effectively brokering between the open source community, education, scientific enterprises, and companies. We have formalized processes for interacting with industry, for interacting with research partnerships. All of that, first of all, it's not the training of a particle physicist. Nowhere in the graduate physics department syllabus do you see any of this. And Brian Granger, who is effectively my project co-director, he's professor of physics at Cal Poly. We were classmates at CU Boulder in physics from day one, so we started our PhDs on the same day, both physicists. He did his PhD in atomic physics, and neither of us has any training in management, in business, and legal issues, but effectively, that is what has allowed us to grow, is that we spend a ton of time doing these things. I remember the very first time we had a conversation with IBM, who was interested in participating in the project, and we showed them, they started asking kind of legal type questions and management questions. We said, oh yeah, let us show you the link to our governance documents. You could hear the relief in their voices, because they basically realized, okay, we can talk to these people, right? They're organized. They have a process. We're not just going to be faced with who on the mailing list is going to answer? Like, how do we engage with a bunch of yahoos on the internet? Because open source, the notion that, oh, well, it's a bunch of people on the internet and there's a mailing list. That's not good enough if you want to build something at this level of structure where you want people to have jobs and careers and long-term strategic vision. You need a little bit more. And the fact that we've done that work has been absolutely key to our success. It has had very significant educational impact. There are a few people in the audience from Berkeley who will recognize that the top picture is taken at Zellerbach Hall. That's basically the opera house on campus. It's the largest, it's the theater on campus. That's day one of Data 8, which is our freshman level introduction to data science, the backbone course in data science that we teach. Those are numbers from last fall. I think right now it's upwards of 1,500. There's no auditorium on campus where we can fit a class that big, so we have to borrow the opera house for the first day of classes. They don't let us teach there, so after the first day of classes, we got to kick everyone out and tell them not to come to class and just watch the lectures on YouTube. And on average, come every other lecture, and it kind of works out. Data 100, which is an upper div course. This is Wheeler Hall, the biggest actual lecture hall on campus. We can fit 750 people there. Last fall, I taught it. That was me teaching with about 800. We were at physical capacity, basically at fire code violation point. Now I don't know what they're doing this semester because they're well past that point. This is all powered by Jupyter. It's delivered on Jupyter Hubs in the cloud. The points Troy was making about access and equity are critical to us. We have a very significant population of economically disadvantaged students. We don't want any of them to be any less than their peers. They can walk into one of the libraries, ask for a Chromebook. They borrow a Chromebook from the library, which they can keep checking out like a book for the whole semester. And with that, they're on exactly the same footing as the rich kid who has the latest MacBook, the latest fancy laptop that they bought yesterday, right? So these tools give us very broad, basing this on all of this open stack that Troy was demoing so elegantly earlier, and I'm going to ask you for some of those gifts, by the way, they're brilliant. They give us the ability to have very, very broad disciplinary reach on campus with this knowledge. Those students come from every major on campus. We're basically reaching everyone on campus. We lower, as I said, the barriers to access, but we also, importantly, lower the barriers for faculty. So it's much easier for faculty to now add data science elements into their existing courses, modify their courses and evolve them because they know that the technical infrastructure is in place to support. There's hubs that are available. Our hubs are authenticated with like the standard campus authentication, so anybody who has a Berkeley account can get access to the hubs. But also the human infrastructure. The data science division under the leadership of Catherine Carson has put together teams of students who help faculty develop modules of content in data science that they can add into the existing curriculum, as well as develop new courses, in addition to these kind of major backbone courses, right? And that program is completely transforming the university in terms of its impact in data science. Now, these are not teaching toys, right? We're not teaching them with a tricycle that is then useless the moment they get out into the real world. The tools we use to teach are the tools of research, and importantly, of open, modern, reproducible research. This is a quote that is in many of my talks. I've used it probably, 50 times at this point, but I continue to live by it. It's a quote from David Donahoe from, look at the date, 1995. And David was arguing that it was unconscionable to publish a paper. David is faculty in statistics at Stanford. He was here paraphrasing a geophysicist, John Claerbout, from Stanford as well. But he publishes mostly in sort of numerical analysis type journals. And he was basically saying, look, it's unconscionable to publish a paper without the code and the data, right? The paper is the glossy sales brochure. It's like the little glossy, but you need to actually give people the inspections book, right? When you sell a house, the glossy one pager from the real estate agent is not what you buy the house on. You buy it on the inspections binder. And that's what we have now. So the inspections binder is called Binder. It was a project originally created by Jeremy Freeman, a neuroscientist at Genelia Farm, who's now at Chen Zuckerberg, and now there's a lot of others. And what Binder does is a tool that grabs Jupyter and lets you take any repository on GitHub or any similar hosting service that has Git access that has explicit dependencies, where in the repo you gave us a file that says, these are the libraries I need to run in some machine-readable form, and there's a lot of ways to do that. And then it automatically containerizes it, puts it in the cloud, so that you can give someone, if you followed these practices that are basically just kind of like computational dental floss and toothbrushing, then automatically you have an executable link that you can give to others. And you may have seen in the news a few years ago, gravitational waves were observed for the first time around. CU Boulder actually had people participating in that experiment. I remember the first time I saw a talk from somebody from LIGO, I thought these people are crazy. You cannot do that. That measurement is physically insane and impossible. You can't measure something across 22 orders of magnitude of noise, but they did. It took them 30 years, but they did it. And on September of 2015, they observed gravitational waves for the first time. This is the figure from the first paper that led to the Nobel Prize in 2017. From the first, this is figure 1 on the main observation paper of that first event of GW 151409, something like that. 150914, it goes by the date. That figure, all of that figure is made with these open tools that 20 years ago people told us we shouldn't build because it was pointless, right? NumPy, SciPy, Matplotlib, the new color map that was developed at the Berkeley Institute for Data Science for better perceptual qualities, all of this work was done with these open tools, and you can run that analysis yourself right now from your phone because there's a binder that has that exact data set. All the data is made available to the public, and that data is bundled up into one of these binders. And so if you go to that URL, you will land in a Jupyter notebook that will open up after a few seconds, after the repos, the containers are spun up, and you can re-execute the analysis of the real data, of two black holes spiraling ever faster into one another until they collide and they merge in the middle, and they radiate out 3 solar masses equivalents worth of energy in the form of gravitational wave radiation, which looks like this. Did we lose it? Oh, come on. We'll try once. Well, it worked the last time. Worked when we tested it. Unfortunately, no. So you'll have to play it on your laptops. You can hear that sound. We tested it earlier, and it did work, but not anymore. You can hear that data converted into sound on your laptop. So the public, anyone, a kid who wants to hear how do two black holes merging 1.3 billion light years away sound, can hear that running off the real data, actually running the analysis, playing on their iPad on the kitchen table. You may have seen this year, this picture. This was the first optical observation of a black hole. Not a gravitational wave one, but an optical direct observation of a black hole. This was an absolute feat of science, of engineering, and of data science, by the way, because I would strongly recommend that you watch some of the talks, especially the talk by Katie Bellman on the statistical construction of the models for reconstructing that image. It's a beautiful tour de force of a combination of signal processing, physics, and statistical modeling, which is really data science at its best. We had the fortune and the luxury that the very, very first public talks that were given about this, the day after the press release, were at Berkeley, one by Shep Doleman here in the physics department, and the day after, Katie gave one in the computer science department, which I don't have a picture of her because even though I showed up half an hour early to the auditorium, it was already full to capacity and they were kicking everybody out, so I had to watch it from the outside. And when they published the papers from this observation, they actually cited and credited all of these tools, NumPy, SciPy, Jupyter, etc. So these tools are now powering the most significant research. That is literally leading to the most recent Nobel Prizes in physics. I'm going to narrow the focus to the Earth, to geosciences, because for a variety of reasons I am now very interested in this. Lindsay Hagee is a postdoc in my group who just got kind of the main award in her discipline for her work, has led the creation of both a set of research tools in her field, which is inverse problems in geophysics for modeling the subsurface of the Earth with electromagnetic measurements. So that's basically a combination of optimization, inverse problems, and numerical PDE modeling, together with building open source tools for education in geoscience, all Jupyter powered. So this goes to the idea that the tip of the pyramid is content. It's what do you give to people and how do you deploy it. So she's done a lot of work in the geosciences space, both on the software tools for the research and the content that will drive the discipline, both in terms of education and in terms of practices of openness and reproducibility. And we've connected with a project called Pangeo that was originally led by Ryan Abernathy, an oceanographer at Columbia, and Joe Hammond, who officially works for NCAR Boulder. He lives in Seattle, but he actually works for NCAR. in Boulder. Pangeo is a wonderful project that has taken the approach of saying the current bottlenecks in science and large-scale geoscience and climate modeling and these kinds of problems isn't anymore the supercomputers or the data. It's actually the integration, the ability to explore, the ability to iterate, because the complexity is becoming crippling for the scientists. You need a level of engineering expertise and resources that makes it nearly impossible to iterate flexibly and fluidly and be exploratory. And they said, aha, but we don't need to build a new thing. What we need to do is glue together the existing machinery that is available, that is open source, that is free, and that is almost there, but it's kind of missing that last bit. And let's put that together. That's exactly the kind of thing that doesn't get funded, that doesn't get people tenure, that doesn't get rewarded by science, but they went ahead and did it. They went ahead and did, that's what needs to be done. They managed to get funding from the NSF. Ryan just got tenure a few months ago at Columbia. This project is one of the most successful things that has come out of the EarthCube Directorate at NSF. And it allows people to do things like that. If you look at that image, someone is basically zooming in into an image, some color blips happen at the bottom, and then a couple seconds later, the image gets sharper. That's a big deal. You zoom into an image and it gets sharper. That's what every image zoom and Google Photos does. The trick is that's zooming on 100 gigabytes of Landsat data over the whole state of Washington. Doing that zoom requires stitching together a huge amount of data, running a cluster to do it, blah, 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 blah. What they've done with Pangeo is make that completely seamless. The little color bars at the bottom is the DAS distributed engine basically sending jobs to all the nodes and managing and giving you real-time diagnostics of where the tasks are and who's doing what and whatnot. That's the point, that the geoscientists shouldn't become a Google Cloud engineer. They should be focusing on zooming on the data they want to look at. And it should just happen, right? And Pangeo has done a phenomenal job of doing that and doing the last mile work with the community and contributing back when necessary. So they've already improved Jupyter, they've already improved that. They've already improved actually all the software, so they actually have contributed to the tech by saying what they needed to do was solve that last mile problem. And so what we did was we just submitted this year a new grant proposal to the NSF, the actual title of the grant is Jupyter Meets the Earth. Couldn't pass on the pun. And it was just announced. We actually haven't even finished the public blog post. We'll probably post it next week. Our start date is technically September 1st, so Sunday or Monday, whatever. And it was a project where we were able, thanks to the pioneering work of Pangeo, to unapologetically say we are building this kind of infrastructure. We do have scientific driving use cases. So Joe is one of the PIs, and he works on the CMIP6 climate data release. So the analysis of that data set on Pangeo will be one driving use case. Laurel Larson, who also has a Boulder connection, she's faculty at Berkeley now, but she got her PhD here at CU Boulder. She's a hydrologist, and so her use case is hydrology. And Lindsay, who works on, as I said, on electromagnetic problems in geophysics, provides the third scientific use case. And we said with those, we will drive developments on Jupyter in various areas of the Jupyter stack. And we were able to basically tell the NSF, this is what needs to be funded. I'm very happy to report that for the first time, this did get well received and well rewarded by the NSF. Because up until now, this is what we'd had. Huge adoption by industry, right? Google has products based on Jupyter. Microsoft has products based on Jupyter. Amazon has products based on Jupyter. IBM has products based on Jupyter. Bloomberg has projects based on Jupyter. Netflix runs on Jupyter in-house completely end-to-end, right? But none of that is scientific, kind of academically supported work, which is the kind of stuff that I do. All of our funding sources have been either private foundations, the ones that Kevin mentioned, or all of these companies, with the sole exception of a teeny little bit of money that I basically wrangled out of DOE, but it doesn't even fully qualify as DOE money because it was internal LBL money, so it's kind of fake DOE, money. Because building this kind of stuff in academia is not great. So these three people are John Hunter, who created Matplotlib while he was an academic at the University of Chicago, had to leave academia to go to a hedge fund. Sadly, John passed away in 2012. He was my best friend, like a brother. We spent a decade building these tools, and he passed away before they really became the success they are today. But he had to leave academia because he literally couldn't support his family by doing this stuff. The stuff that now is powering basically the last string of Nobel Prizes in physics are coming from his stuff. He basically couldn't make a living out of it. Travis Oliphant created NumPy, which is the core foundation of the entire scientific Python ecosystem, was denied tenure at Brigham Young and had to leave for industry. William Stein is a number theorist. You were mentioning number theory. He's the creator of a project called Sage, which uses Python and the open source Python ecosystem, but basically for pure mathematics. Fully tenured faculty at UW, full professor, was tenured faculty at UC San Diego, went to UW. I think when William graduated, left Harvard's postdoc, he had 5 offers with tenure out of the gate. I can't do this. So this is a blog post he posted a few months ago, basically saying this does not work. This does not work. I can't do it. I can't sustain this open source effort in academia. He founded a company to try to make it work. Eventually, his leave time ran out at the university, and he announced, I'm leaving. So I have decided to resign. I'm leaving academia. This is basically somebody who was kind of at the literally at the very top of his field with tenure, with grants at one of the top math departments in the country, and couldn't make it work. Because all of this stuff, which now powers all of research, exists pretty much in spite of the system. Not just not thanks to it, but almost in spite of the support of the funding infrastructure and the academic incentive system, including hiring and tenure and promotion and all that. Indirectly, it's true that the external funding has, a lot of money has been funneled under the covers, wink, wink, not, not, program officers don't look, and as long as some papers come out of the grant, people write software, but that's not how it should be, because those people are still paying a huge price. There's a huge incentive in the software funding pipelines to say, well, go build a new thing. If the previous thing doesn't work, go build a new one. And we end up with not 2, but 10 highways, half built, all of which take us to the same half spot in the middle of nowhere, and not a single one that actually takes us to where we need to go, right? That's the beauty of what the Pangeo team did. They said, we're not building a new one. We're going to patch one that makes it all the way to the end with the pieces of the existing ones. But in every metric you can think of, there's a huge contrast and a brutal tension between how the production of this kind of knowledge works and is done in the open world, and how academic incentives work. And I won't go through every one of them in detail, but you can pick your favorite one where you said anyone who operates a little bit in this space has one of these things, which is a personal point of pain for them. And what we're seeing is that we're beginning to recognize that tools like AstroPy in astronomy, DiPy and NiPy in neuroscience, SymPeg in geophysics, MedPy in meteorology, etc. In the domain disciplines, the open source packages that the people in that discipline use and are beginning to publish papers from are beginning to be a little bit more recognized. That is getting better. That is starting to get better. The astronomy community has been particularly good at rallying around AstroPy. They publish papers around it. The community kind of formally says astronomy needs this, and enough people high up enough the food chain recognize that. But on top of the core language, which in a sense is kind of not our business, we interact a lot with the core team, but it's maintained by a separate team of people, there's these 2 layers of what I call these core very generic tools like NumPy, Matplotlib, IPython, Jupyter, and slightly more specialized tools like image processing, performance, machine learning, scikit-learn, image processing, but that are still very domain generic. They do kind of one job, but that is useful across many domains. These 2 layers together form this, what I call the domain agnostic backbone of today's science. And that stuff is, it's not real computer science, it's not real research, it's not real work, it's not novel, it's not transformative. Good luck submitting grants on that stuff to the NSF. They get chewed up and spit out like they're garbage, right? Because it's nobody's problem, right? And yet, without that, the rest can't function, it can't exist. So what do? There are organizations that are trying to fill the various gaps in this space. The Carpentries was already mentioned, brilliant organization that tries to fill the skills gap in training and education, kind of beyond what the university is providing in this space. The career paths problem. What do people who have a scientific training but want to do this kind of work, what do they do for a living? If they don't quite meet the criteria of being faculty or and if they don't want to go purely into industry, which will welcome them with open arms and give them both interesting things to do and pay them handsomely. Well, the notion of research software engineering as a career path is gaining hold in the US. It was really developed and evolved very, very thoughtfully from mostly the UK and the Netherlands, but with leadership in the UK, the Software Sustainability Institute in the UK. There's a really good team in the Netherlands around this. But now they have a new kind of worldwide website. There's a US chapter of it, and this is getting kind of more formalized as a structure, and I think this is a very healthy development. As I mentioned, Focus is a 501c3 that kind of bridges the gap between the open source community projects, companies, and maintaining those communities, the practices of those communities. It also provides fiscal sponsorship. So for example, if Jupyter needs to take a donation or a small grant that isn't specific to Berkeley or Cal Poly or one of our kind of more academic centers, it can go to Focus, and Focus can basically serve as our umbrella legal home from the IRS perspective, without any of us individually, either personally or institutionally, having to be the one that kind of manages all of the project. Mozilla is, interestingly enough, an institution that is doing a lot of work on the problems around management, around leadership, around community growth, and the human aspects of this. And so they have an open leadership program that is very, very interesting and that operates in multiple spaces, from like digital rights in Africa to open science for climate science in Scandinavia. So they have kind of a huge spectrum of activities. The problem of bringing academic credit and academic recognition to software artifacts, to computational artifacts, to educational open artifacts, the kind of things that we've been discussing today, is one that's tackled by a pair of projects, Joss and Jose. The journals of open source software and open source education have been led by Arfin Smith, who's at the Space Telescope Institute, and Lorena Barba, who's faculty at George Washington. And these are effectively academic journals that make it very easy to publish and with a very strict, very rigorous, but very streamlined review process and model for open source tools and open source educational materials, but giving people a DOI, a citable artifact, kind of a more recognizable output that can help bridge the gap with traditional metrics of academia. On training, there's a model that has been evolving phenomenally, actually out of the same Moore Sloan effort that Kevin was talking about this morning. So this was born out of the collaboration between Berkeley, UW, and NYU, mostly led by a team at UW called Hack Weeks. And it began with Astro Hack Week years ago, and the idea is to have training where you mix from undergraduates to senior PIs. They've actually developed a very sophisticated model for optimizing diversity across multiple lines, not just gender, ethnicity, but also career paths, skill sets, seniority, everything, to put together in a room a set of people around kind of a given domain for a week in a combination of learning and hacking and doing things together. Astro Hack Week was the first one, but now there's Geo Hack Week, which is next week in Seattle. There's Ocean Hack Week, which is finishing today in Seattle. There's ISAT2 Hack Week, which was about 2 months ago in Seattle. I taught at that one. There's now Neuro Academy. They had to change the name because they made it 2 weeks long. The UW folks actually got a 5-year NIH grant to turn it into basically a 2-week summer school with this model. And so, but because it's 2 weeks now, it's not called Hack Week, it's called Academy. It's absolutely brilliant. And these people have actually written down, there's a paper on PNAS with the formal kind of educational model and their approach to this problem, that if anyone is interested in these ideas in education, I strongly recommend that you go and read that paper from PNAS. It was led by Daniela Huppenkottel. She's an astronomer, but the co-authors are a mix of astronomy, cryoscience, ecology, astronomy, and neuroscience. All these folks from this Moore Sloan environment. But these tools are facing what Tracy Teal, the director of the Carpentries, calls catastrophic success. And this is an economic problem. A paper published in 2015 took a look at what had happened in astronomy, which was a world completely dominated by one software tool called IDL in the past, mostly, and with something else called IRAF. And by 2015, it said, today, Python is by a wide margin the most popular high-level language in astronomy. And this was a huge shift. I mean, 10 years prior, people would have laughed at you. That means that IDL, or in other disciplines, MATLAB or Mathematica, are not as dominant anymore. And how much changes by field and whatnot, but largely this kind of change is happening throughout. MathWorks has over 4,000 employees. Wolfram Research has 800, smaller but more specialized company. IDL belongs to a company that has about 17,000 employees. I'm sure the IDL division is smaller, but still, it has behind it the resources of a multinational corporation with almost 20,000 people in it. Right? That's a huge amount of financial and logistical resources. What's the equivalent in open source? What is the actual business model? Those people are not stealing anything. Those people are working. They're engineers writing code, maintaining it, documenting it, right? The open source community is not some like magical pixie dust of people who eat air and live in the clouds and produce code, right? There are people like you and me who still need a job and they like need to put clothes on and food on their table. How do we do that if we're going to absorb this economic problem, right? So the federal R&D budget is give or take $180 billion last year. What fraction of research touches computing? In this particular survey, they asked that question of astronomers at least, and the answer was 100%. So everyone, every single astronomer said, I can't do my job, not without email, but without research software, technical computing software. The answer, that was the one time I've seen in a survey a number that comes back 100%. Not a single individual answered no. So I would argue that 10, 30, 50% is probably an underestimate of how many scientists today couldn't do their job if they didn't have a computer, other than a computer that could do like email and word processing, right? $200 million is 0.1%, not 10, not 30, not 50%. 0.1% of 200 million is of 200 billion is $200 million. I would argue that the bang for the buck in terms of return on investment of putting $200 million per year into the open source ecosystem, the ROI is gigantic. It's absolutely huge. Plus, it's mitigating that economic catastrophic risk that has been created by making this transition. This success has actually opened up a huge window of risk that no one is mitigating, and I would argue that mitigation is really, really cheap. The trick is, 200 million annually, well spent. You don't write a 200 million check with the payee being the internet. Good luck, right? You don't do that, or Facebook, right? Or GitHub, or a mailing list. So how do you spend $200 million well on these kinds of communities? That's a business problem, that's a management problem, it's an organizational problem, it's an ethnography problem, it's a social problem, it's a people problem. We've learned some lessons. We have some understanding of what are some of the features of projects that are successful, that are effective, that are resilient, the way they engage their community, the way they manage their contribution pipelines, the way they build capacity both for short-term effective action and strategic thinking, the way they have recognized that code is only a part of the job and they have built the rest of their human infrastructure and tapestry. So projects that effectively have recognized that they are complex organizations and not just 3 random people writing software on the internet, that it's a lot. The real job is much more complicated than that if you really want to have impact at a certain level. Those are the features of organizations that do succeed. And that's what this money should target, but also should encourage the building of. And this is just observation from our experience. And I would love, and I think there is an opportunity for people, for example, who think about business and organizations to contribute here. Recognizing that projects that are capable of strategic vision are so because they have people who can devote the time to that kind of effort. Basically, you have to professionalize and recognize as full-time work those parts of the job, not just debugging on GitHub at 3 in the morning, which is also important. A very important point to me is that recognizing this as a problem of professionalization is actually being inclusive. Because if you say, oh, volunteers can do this job, nights and weekend people can do this job, you're saying, well, people who can afford to volunteer can do this job. If you have kids, if you have 2 jobs because you can't quite make ends meet, if you don't have financial, personal, health, on whatever dimension, the freedom and the luxury and the privilege of, yeah, I have my nights and weekends free to myself to spend them on GitHub, you can't participate in this economy and in this world. So recognizing that this can and should be a job, which is allocated, which is recognized, and where people are included, is actually inclusive, and we should do it. There's been work already studying this problem in a more systematic way. Anyone who's interested in this, the first thing to read is Roads and Bridges. It was a research study funded by the Ford Foundation, written by Nadia Egbal, who works at Protocol Labs in San Francisco. Brilliant piece of work, not focused on science. It was taking the larger view of open source in general on the internet. Absolutely fantastic piece of kind of background baseline research on this topic. Nadia herself has now been looking a lot at the work of Elinor Ostrom, who died already. She passed away a few years ago. She was an economist who won the Nobel Prize in Economics in 2009 for her work on models of governance of shared commons that could potentially, and her work is empirical, it's based on research done in the management of California watersheds in the 70s. How can communities avoid the traditional pitfalls of the tragedies of the commons, right, in the successful and sustainable exploitation and maintenance of a commons? And what are the identifiable and recognizable features and processes of management that lead to sustainable success versus kind of the death by the exploitative tragedy of the commons? So I think this is extremely relevant work for this kind of very distributed multi-stakeholder environments that we have, where you can imagine that the business unit at Netflix has a very different incentive model that I have as a professor at Berkeley, or that my colleagues have at a DOE national laboratory, right? Each of us wants to contribute, but for that to be a reality beyond, well, nights and weekends, as I said, then it has to align with our actual jobs, with our actual, effectively, organizations. And so how do you align all of those diverging kind of local interests towards this kind of long-term common effective goal? So it's basically back to this. It's recognizing that open source software is a hell of a lot more than software, right? And that we have to recognize this, treat this as a complete problem where these are the needs and questions that need to be addressed. Economic needs, questions of governance, questions of career paths of institutions, of actually even like job titles and job codes and promotion manuals and tenure manuals. I'm actually working on that at Berkeley. Now that I have the privilege of being there as a tenured member, I'm like basically trying to put changes into the tenure and promotion processes for faculty, and the design of these kinds of multi-stakeholder, very open organizations which are different from traditional businesses. So thank you for your time. Thank you for listening. And I want to thank the local team at Berkeley. The whole Jupyter community is big, but this is the local current and former team in the kind of Berkeley area that I work with, and who really deserve, in addition to the rest of the project, who deserve all of the credit for making my life possible. Thank you very much.
I think we can spend another 5-10 minutes to take questions. We are recording this, so if you don't mind.
Hi. I was wondering, I was just watching a program on last night, and it was talking about specifically making more research money available as a percent of GDP, and they wrote a book called Jumpstart America.
I think I heard the same program. I was on NPR yesterday.
Yeah, exactly. And it was also on PBS NewsHour in the evening. So what do you think of that? And is that kind of aligned with what you're saying as well? And maybe could the communities kind of come together and request better?
Absolutely. If that book goes anywhere, I will be cheering and contributing in any way I can. 200 million is 0.1% of roughly 200 billion. That 200 billion is 0.7% of current GDP. We, the US, I'm not American, but the US used to be at 2% of GDP, down to 0.7%. So you can think that they're asking roughly for a tripling of the R&D budget. So it would be, instead of 200 billion, closer to 500 to 600 billion. The same 200 million would make a difference. 500 million would make a better, would be bigger. So absolutely, yes. I think in this case, the critical question is, though, to spend it well. Because there actually has been, on certain things, the federal government has spent money on software projects, and a lot of it has gone down the drain, because it's been those like roads to nowhere kind of thing. And so the trick is really, and the program officers, by the way, they're thoughtful people. They're not idiots, right? And they're not evil. They're just operating under a system that has very awkward and old constraints and that is very slow to adapt and hasn't fully reacted to this new reality. But they're eager to change and to improve, and they're interested in talking. This lecture is a modified version of a talk that I gave 2 weeks ago at NSF headquarters to the CISE directorate. And they invited me to talk about this, and they were extremely receptive, and it was a very productive conversation. So I don't want to demonize in any way the federal agencies. They are good people doing the best they can. It's a tough problem, and the ground has shifted really, really fast under everyone's feet. So the question is, how can we help them make those decisions better? Arguments like the amounts definitely will help, but also the how do we do it? And as I said, this is something where I think people from organizations, from business, et cetera, have a lot to contribute.
Thank you for that great talk. In terms of the funding model for this, you said you work with Anaconda and you have the Kubernetes system at Berkeley as well, and people can use that outside of Berkeley, and there's a charge for this. And I'm wondering if part of the solution to support these open source software tools and these developers and people that are in the like somewhere existing in the ephemeral world between academia and industry and the labs is having these institutions like Berkeley and just other universities at large look at marketing the research and tools that are coming out of faculty departments and research groups and institutes to professional organizations for the training of professionals and having some sort of fee-based model in place to get revenue to support this line of researchers in these institutions. Because you have these annual big workshops with like Matplotlib, and I remember there was one in Austin shortly after your friend passed away. I was a postdoc down there when that happened. So I know that there's some of this, but do you think that would maybe be a more immediately successful model to push than waiting for a certain administrative changes at the government level?
So I think it's not a matter of either or, but of and I think we should try more such things. There is a point where running the business becomes the full-time job, and then you're not doing the work anymore. So it's a tricky balance to hit. You also have to be careful in how you engineer those organizations so they maintain a healthy relationship with the rest of the open community. It's very easy in these communities where when everyone is contributing openly to a common good, if one actor begins to profit directly from it, it's very easy to disrupt the contribution dynamics. It's a really interesting and actually well-studied problem in this space. So it's a non-trivial question, but the answer is yes, and we are trying things out. There's actually a recent post on our public discourse website for Jupyter coming from Canada. So Canada actually has national Jupyter infrastructure. So Compute Canada, which is their equivalent of HPC for researchers in Canada, struck a deal with PIMS, which is the Math Institute in Vancouver, the Pacific Institute for Mathematical Sciences, and they've deployed something called Syzygy, which is basically Jupyter for any Canadian researcher. And the same team at PIMS partnered with the Alberta provincial government to create a second project called Callisto, which is Jupyter for K-12 in Alberta. So the Syzygy is kind of university and science research, HPC, for all of Canada. Callisto is K-12 with curricular development. And what they're finding is catastrophic success. They're being so successful that they can't keep growing this because it was like a particle physicist and a mathematician were doing this. And so they decided, what do we do? And we brainstormed ideas, and they've just posted on the Jupyter Discourse website a plan for trying to build a network of national nodes so they can go serve a national market and go after national funding. They're going to try in Canada, but we're thinking about doing the same in the US and potentially others in Europe, of entities that could basically provide services and have an actual operations role that can be a business-like entity, but that would be explicitly designed to contribute back. So it's not quite starting a training company or have the universities directly be the ones that charge, but something tells me that that model of a network, a collaborative network of similarly structured entities might be more successful. You're welcome to, like we're trying to now have this discussion in the open. We did some brainstorming a couple months ago at Berkeley, but we said, let's move this into the open so it's on a public discourse. There's a blog post on the Jupyter blog detailing these ideas, and I would love to talk like openly about it.
Let's take one last question.
So I was wondering if you had thoughts about how to make sure like methods and tools are available across languages? I mean, so a specific example. So I usually teach regression. I use R in general, statistician. There's a lot of statisticians have worked on that. So if you want to do statistical things, packages are available, right? So I'm thinking like diagnostic plots and things like that. So next semester, the person who wants to teach it says, I think I want to use Python. I'm okay with that. It's a great language. But the same tools are not available. So now you have to like reinvent the course, if you will, in order to do the same stuff. And I know I had students last semester in Bayesian statistics. They wanted to use Python for running the models. We're using Stan as a backend. So Stan has Python front end. They have an R front end. That's great. Then when it once again came to like something like plots, R's abilities were way ahead. And it makes it challenging as teachers and who want to educate our students to provide them with tools when suddenly the student who, you know, they only have a few years of training needs to become expert in 3 or 4 different programming languages to do what they need to do. And it seems like Pangeo was kind of trying to do something like that for geosciences, maybe. I don't know. I'm just going off your talk. But what are your thoughts about that? Like, how do we spread that so that, you know, the tools are available across languages?
It's a very tricky problem. There's no easy answer for it, honestly. I think some of the fact that Jupyter is a polyglot tool can help to some extent in 2 ways. First of all, you can deploy a Jupyter hub that has both R and Python kernels so that people can create notebooks in either, and at least the language is different, but at the level of the workflow and the notebooks and that part, you're on common ground, so that can help. Number 2, if it's a mostly Python workflow with some R in it, the IPython kernel has very good capabilities for basically sub-processing R with the R magics and basically having blocks of pure R syntax with very minimal contortions. Like you just put %R and you type R code and you can pass data back and forth. So it makes it fairly seamless, but you're still dealing with 2 languages. Because honestly, to some extent, this problem is never going to go away. And tomorrow it's going to be Julia, and then in 5 or 10 years it's going to be something else. Programming languages keep evolving because our problems evolve, because the way people want to approach problems evolves, and they are tools, and we will continue having more than one. There's no, I think, interoperability at the level of the human narrative, which is one level where having the common notebook infrastructure, that's why we work so hard with many communities to make it, to say, yeah, tell us what we're missing and we'll do it so that we can share at the human level, right? Interoperability at the level of data formats, the kind of thing that Amy's talk was discussing earlier, that's really important because if the data layer is common and the human layer is common, the language that mediates between those two, okay, we can negotiate a little bit on that. On things that are critical, there's some interesting technical work that has been done. A team very connected to Jupyter that has a startup in France called QuantStack has been building a stack in C++, designed from the get-go to be very easy and very cleanly bindable in Python, Julia, and R. So that the low-level layers are it's called extensor and the extensor stack, that the low-level layers are very clean, extremely modern, well done C++, but designed to be bound interactively with any of the high-level languages. But obviously that's kind of its own set of tools. On this one, there is no magic bullet, and I don't think there ever will be. So practices of translation, potentially of having effectively parallel versions of teaching materials, unfortunately. The carpentries have ended up doing that. The carpentries have literally versions of their teaching materials, some in R and some in Python. And yeah, it does create a double maintenance burden, and you can't quite have exactly the same thing because there are things you need to say, even in the human text, that are relevant to the programming language, right? Or you discuss features that emerge from the analysis. So it's an inevitable burden of the fact that humans like languages, like we like human languages. Right? I was born in Colombia, I grew up in France, and now I live in the US. I got to type in all 3 languages all the time.
Thank you, everyone. Let's thank our speakers.
Thank you very much for your attention.